So what I will be talking about is the work that we are doing in our group in Amazon. So I'm part of Byron Cook's team in the automated reasoning group. We are further part of AWS security, so we are mostly concerned about the internal security of our software stack that we have. Before I go any further, I would like to introduce you, just in case you do not yet know it or you have seen that for the first time, what's referred to as the shared security model. So if you, in public cloud offerings, as Amazon Web Services is doing that, the security actually rests with two parties. One is Amazon as the provider, but also another part still rests with the customer. So there's the top part, where customers are actually themselves responsible for keeping their systems up to date, keeping their systems secure, configuring policies appropriately so that access is limited to those who actually should have access to that. Some of you, I think there's a few folks from the US here, especially those will have learned about some recent leak of voter data, which is, yes, people use resources and then don't configure it properly. That essentially is a problem that they have to worry about. Nevertheless, we will always try to help our customers and guide them. Personally, I have actually received this morning an email for my personal AWS account that some of my buckets are publicly readable, so which is intentional in this case. They are hosting websites, so that's fine. But those systems that's what the customer needs to care about. The provider does not really know what the purpose is of what the users want to achieve with the systems, and the provider cannot do it right. That's what the customer has to do. There is, however, also the underlying infrastructure that Amazon provides, that Amazon maintains, and that's the part where the provider actually has to make sure it is secure, systems are kept up to date, so that the customers can actually rely, as they build on that infrastructure, on having a system that is as secure as possible. I believe this setting is the same for various public cloud providers, so there's nothing particularly Amazon specific in here. The work that our team is doing lies mostly below that bar, so we are mostly internally facing. We do, however, also work on systems that will eventually reach customers later on this year, which live in that upper part. So in particular, also the email that I got this morning is quite likely actually triggered by a system that our group has built. Because what we do use is, we're called Automated Reasoning Group, but really we use constraint solvers at times to actually reason about policies and prove that they are safe or that they are actually more or less permissive than something else. So in that upper part, wherever our contributions are, we heavily use constraint solvers because that's the way we believe this should be done, and that's also something that we have essentially newly brought to the company. And that's just where we can gladly just use existing technology, which we will learn about later on this afternoon, and just build on SMT solvers. For the bottom part, however, I'll just give a high-level view of what the system might look like. So as we want to provide resources to customers, we essentially provide virtual machines. When we do provide virtual machines, that means there is some underlying hardware. On top of that sits what's usually referred to as a hypervisor. And on top of that hypervisor, we will actually have the guests. That could be one or more customers using the same physical machine underneath. And what we would like to make sure is that those guests cannot interfere with each other. So of course, as a customer to this platform, you would assume that whatever software you're running, and as much as basically you can see, is properly isolated from any other customers who sits on the same, possibly physical machine. That is also an area that has seen a number of exploits, or at least security advisor is published on a fairly regular basis, so we need to make sure that's kept up to date. Now, it would all be nice if the system and the infrastructure would just be all that easy. So our research community, you will find quite a few people who have actually published work proving parts of that stack correct, studying at least fractions of that. But the reality, of course, is that we not only have somewhere here a box that is actually virtualization, but all that interacts with database systems to manage this. You will have file storage living nearby. You will have a network in between. And any of these components that are involved may be susceptible to attacks. And any of those components, if attacked, may actually make that entire system fall apart. So we need to make sure that not only is the fairly local part, which is actually just on one machine, safe, but also the entire environment that this lives in. That much said, it all seems a fairly big software system. So it is certainly challenging. What makes this, unfortunately, quite a lot more challenging, and that was some of the bits that I hadn't quite expected, is the requests that you get. And when I say customer here on the slide, that does not necessarily imply that that's a person outside the company. This may as well be an internal customer. So the statement you can all read, I would like to get a guarantee that there are no security bugs in the software. Well, who wouldn't, right? Anyone heard of the halting problem? Well, the problem that we face is, well, undecidability is part of that problem. The underlying problem, to a larger extent, is actually the lack of education. And that does coincide with what Tom has talked about. The people we are talking to are hardly ever formal verification specialists. In many cases, we might actually have PhDs. They might have PhDs in their field. But if they are developing a virtualization stack, then it's quite unlikely that they have a PhD in formal verification. But rather, they will actually have worked in those various areas of operating systems. And they are certainly much more specialized and specialists in that very area. But if you talk to them about formal methods, then they will just stare at you. And yes, if they have gone through a computer science degree, they may vaguely remember that there was something about undecidability, but that's about it. So the problem that we often face is, okay, well, you have this magic technology. Can't you just prove all our systems correct and make sure all the bugs are gone? So we need to get across what is feasible, what is actually reasonable to do, and what also do we need in terms of collaboration from other people to apply any of the methods. Philippa has earlier mentioned that I've been working on CBMC, and it's no particular secret that part of this work also includes, but it's not limited to, applying CBMC. So we do have tools that to an extent work. Some of them scale, others don't scale as much. But they're still not quite the silver bullet. And even if we had that silver bullet, do we actually know where to fire it? So you need that collaboration, you need that ongoing work together with other teams. To an extent, I'll get back to that quote, but that's just a challenge, and that is one that I certainly hadn't quite expected. Now, what I had expected was that we would be working with a lot of code. Yes, we are talking millions of lines of code. So when I joined Amazon just about 2 years ago, I felt prepared for that. And I was very naive, of course. Well, why was I even thinking that I could possibly be prepared for that? And an experiment that I had been conducting before in my academic world, that experiment still continues, is run software analysis at the largest possible scale, or what I thought as much as I could achieve. So I ran it on open source software. I took all the software that's part of the Debian Linux distribution. Debian ships at the moment about 1 billion, it's actually more than 1 billion lines of source code. So that's of course not just the Linux kernel, but that includes all the way to all the user space software. And a fairly large quantity of that is C code. So my focus on that is the C code portion of it. And that's about 450 million lines of code. Now, so that felt at least, okay, large code I've done before. We can talk about the depth of that, but yeah, dealt with that. Also fairly diverse software, actually. So if you look at a Linux distribution that features a lot of very diverse software, from some low-level bits to, of course, lots of high-level software. And that I had all played with. There are a number of challenges in doing this, which I'll elaborate on. A few people in this room have seen this slide before, since this is actually past work. So the setup that I had for my Debian work is I would be able to compile and link individual source files, link them together properly to enable program analysis. All these are stored. That's actually publicly available, and there are a number of publications that are already using that, so publications that I'm not even involved in. And there are several workflows, one of which includes eventually running a bounded model checker in a very bounded setting. So I just unwind loops once, because scalability of bounded model checking isn't quite that great. But it can be run, and you can actually get some results. In fact, I have reported more than 800 bugs. They're all publicly available. And I could go on reporting lots more issues that have been detected, and I just haven't actually gone through the steps, the somewhat manual process of turning a warning or issues reported by software analysis tools into actual bug reports. So that I had done, and that I felt could actually prepare me for doing that work in industrial setting. Indeed, I actually expected a much more streamlined setup, a system where I would just plug software analysis tools into an existing pipeline so that various bits of source code will be subject to program analysis. We know that the team at Facebook is doing quite a lot of that, and we'll be hearing about it from Jules later on. So I thought, well, can't be too hard to do that in Amazon, is it? So what I had, of course, run into was a number of, so here's just numbers, so about 1,700, 1,800 counterexamples that CVMC reports. Many of those I haven't even reported as bugs yet. But also a number of issues in the tooling. And what I did was, well, okay, I've got, in Debian there's 26,000 packages. So I mostly just ignored those failures, because I could still have loads of good results on other packages. So that was just seemingly safe to do. And what it seemed, okay, both if I look at the virtualization stack in Amazon and the open source code, I have to deal with fairly large quantities of source code. So we're talking way more than 10 million lines. In both these settings, there's a complete absence of specifications. So the only specifications I can possibly use is very generic properties such as memory safety. If you're talking to the open source world, you might say, well, okay, developers can't be bothered, and it's fairly hard to get in touch with them. They can't be bothered to write any specifications. If you're talking in a corporate setting, you may have access to all these developers, but they are essentially just busy. They're always busy, and they'll never have time for providing you with further insight that you need. This is a major problem, and I'm not going to present a solution to that. If anyone has a solution, please let me know. that is a limitation. And finally, and Tom has elaborated on that very nicely, is the limited knowledge of people about formal methods. So that's first of all how to use them, and that's secondly even what are these? What can they possibly provide us? How would we best employ them? How would we effectively use them? All that I think is to some extent make those tools easier to use, and the other bit is just more education. So most people who have gone through a computer science degree, and probably almost all the people in this room are an exception to this, will not really have seen a lot about formal specifications or formal verification. You can, of course, complete a bachelor's without ever hearing about that, and probably also a master's. So that absence of knowledge is for now just reality. If all that knowledge becomes more widely available, then more methods could be applied. There are also things that I figured are quite different between the work I have been doing in Debian and what I'm now doing in Amazon. So what I have mentioned, and I'll briefly repeat that, is that it's now a lot more about the depth. So instead of talking about 26,000 different packages, and each of them finding some bugs and being fairly happy, there is now a much smaller set of packages to be analyzed. But there's no way of just saying, well, okay, I just don't care about that particular package. The direct access to developers is good, but also that means those people will ask you for, okay, how quickly can you deliver on this? So there's always talking about service level agreements and, well, if we run this, can we get an answer within 5 minutes? Can we get an answer in half an hour, etc. What was surprising to me is how difficult build integration can be. I have worked on this quite a bit, and that's something that people in formal methods may ignore at times. Most of you may have seen a makefile, and integrating with that is something we know how to do. Automating this and dealing with various different build systems is also something we have learned to do. But when that was actually very easy to do in Debian, it proved surprisingly hard in my Amazon world. The development process, I have just had a brief chat with Roderick around lunch. Well, I guess we're calling it an agile development model. You may also call it chaos. So there's people involved and everyone just trying to move as fast as you can. The one thing that also many other parts of our company even would hope for is there's a time where you just freeze, and that's the product you're going to ship. The product is actually shipped. Some of you may have used it, but it just continues to evolve. So if you perform whatever analysis on a certain date, that result may no longer be valid the next day. So unless you integrate with continuous integration properly, your results are invalid at any given time, basically. What is something to be aware of is that mix, we do use a lot of open source, but of course there are also internal parts. So in Debian, everything's open source, of course. If we move into the Amazon world, we have that mix, which means sometimes we know who the developer is, sometimes we actually have a hard time getting in touch with the developer. And finally, and that's a learning that was to an extent painful. So as a formal methods person and a person who's academically done program analysis, to me, kind of all bugs are equal. So if I have a software and my software analysis tool tells me there's a problem here, then I'll try to fix it and move on. And that's bug count increased by 1. Moving into a corporate world where a lot of people have a security background of various kinds and with a number of 3-letter agencies behind them, priorities are different, and not every bug is equal. So you either teach your tool to find the hard bugs, or, well, hard bugs, the bugs that they care, or you do some manual triaging, and that's something that that we're trying to learn. I think we're not quite there yet. So I've briefly touched on that. You've seen the slide before. So what really is, to me, a huge difference between, and also really the key difference between academia and what I now do in Amazon, I'm to an extent using the same tools. I'm applying it on large code base, but I can no longer just say, okay, I'll ignore those few packages because they have various problems, and I'll just be happy with the result on the other 20,000. Now it's, here's your package, work on that. If your tool breaks, fix your tool, make sure it works. If you think your tool is unsuitable for that task, make your tool suitable. The task is set, and moving to different benchmarks is not an option. The absence of specifications, that really limits what we can actually achieve. So we've got tools which may at times even be able to prove correctness for the few specifications that we have, which are generally the built-in ones. We have just recently completed the analysis of some BIOS code. So that's really the first stages of booting the system. And we have essentially proved memory safety, which is fine because we also found 2 bugs, and those were considered serious, so it's kind of good. But what now? We know that we have a memory safe boot process, but we actually don't know, because that's also in the context of trusted platform modules. So are we actually booting the right system? Do we trust any of the cryptography really? All that we don't know. And it's good that we can do proofs, but unless someone actually provides us with good specifications, our proofs will always be, to a large extent, fairly boring. And all the interesting properties that we could possibly prove are almost out of reach because, well, if people don't talk to us, that's very hard. And the point that I think I probably don't have to go into depth very much because Tom has really done a great job on this already, is that education part. And that's, many people in here actually in this room have an academic affiliation. And to all those of us, it's really a call to working out how we can actually bring more people with the right knowledge into the business. That one aspect is just educating people. And then also, well, companies can only do whatever they have the personnel for. So one reason in Amazon we are using CBMC is because I'm there. If me wasn't there, we would probably be using something else or nothing at all. Facebook have gone a different route. They just acquired an entire company. Otherwise, Infer would probably live somewhere else at the moment, and Facebook would not be using it. So you can only do whatever you can hire for. If you can't hire these people, so if there aren't sufficiently many people who can actually do proofs, then companies won't actually set these up. Even if that technology proves to be extremely successful, unless there is a good stream of people coming in, they just won't be able to apply it. And with that education comes this triangle, which you may have seen elsewhere. It's actually the person who first introduced me was Martin Brain, who was in Oxford. Because of undecidability, you can't actually have a scalable, precise, and fully automatic solution to the problem. So you can choose 2 of them, and whichever 2 you choose, that will guide you in different directions. So if you want scalability and precision, you will almost always be doing some compositional form of highly manual proofs. If you want precision and automation, you might end up with a tool like CBMC. If you do automation and scalability, you will use some data flow analysis, which has probably a fairly high false positive rate. So in order to cope with those large amounts of code, we ended up on the bottom line in many cases. But then we are currently trying to find ways of improving the precision of those results having a scalable analysis in place. I'll just give a sort of verbal overview, and I'll conclude then at that point. Sorry, of what we've found also. So has the effort that we've spent in the last 2 years in this stack been of any use? So the question is, how do you actually prove to a management what value you provide? So how is formal proof actually good? What's the use case? What is the business case behind that? The simplest metric is counting the number of bugs, which is in a way against the let's do proofs of correctness, because what we've actually done, we've proven that it's not correct. It's a simple metric, and it's one way of measuring success. In the long term, we'll have to find better ways of doing that. But that's really the key challenge that we have initially faced. I think our team has overcome that, but initially it's really give us the good business case. So that team is an experiment. Show how you can actually contribute to the business. We've found around, I think the exact number now should be 90 bugs in the virtualization stack, or the parts of the virtualization stack that we've looked at. We have used CBMC, and that's probably 5 of the bugs that have been detected using CBMC. We are using 3 different data flow analysis tools, some of them commercial. We are also using Infer. Infer has confirmed some of the bugs that others have found, so it's just in the order in which we've run the tools. We are now working on having continuous integration with all these tools to make sure that as the code base evolves, we will continue to confirm the absence of these bugs. But that proves challenging, as I've mentioned before. And what is the other challenge? So the technical challenge is doing the continuous integration. The management challenge is convincing people that those bugs that we find are actually high severity ones. So we've classified them initially, and we had confirmation from engineers that I think 20 of our 90 bugs were high severity. Further discussion then with security people says, no, this is nothing's here high severity. So it's really, that's a lot of human and a lot of high judgment of when is it high severity or not. We've got follow-up work to formalize that, but I won't have neither time to talk about that today, nor are we actually that far that we can properly talk about that. So to fully conclude, the good news for us is that we have found and those bugs are actually fixed. The bad part is that for open source tools, we can find bugs, but often they don't scale, so we know very little. What's really ugly is when we go towards data flow analysis, commercial data flow analysis tools, we actually know nothing. They give us some bugs, some of them are false positives, some of them are true positives, and in other areas, they may actually miss bugs. And that's one of the worst situations you can be in. You run an analysis and you actually have no guarantees either direction, neither on the false positive nor on the true positive side. And yeah, the reality includes quotes like, we can talk about guarantees, do we get guarantees? And well, you know, we will never be able to give those, but other people request them. So it's hard times, but also it's fun times. Thanks, everyone.